Okay, so what are the effects of structure on acidity? So one of the first considerations is bond strength. And if we look at hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid, we see that hydrofluoric acid is a weak acid and the remainder are strong acids. And this is a little unusual because if you look at electronegativities, fluorine has much larger electronegativities than iodine. So why is it that we have the acidity seems to be inversely proportional? And it turns out that the bond strength of hydrofluoric acid is much higher than the bond strength of hydrogen iodide. So the effects of structure on acidity, bond strength plays a key role. If the bond strength is really strong, it will not want to dissociate into its component ions. Another way you can also look at it is looking at, besides bond strength, the size of your atoms. As I increase in my acidity, we also find that what we're doing is we are increasing the radius of my ion. So because of that, the negative charge on the iodide ion right here is going to be distributed across a much larger volume than the charge is distributed over the fluoride ion. And so because that negative charge is distributed over a much larger volume, much larger atom, it's more diffuse. And so the iodide can stabilize that negative charge much better than the fluoride ion. So bond strength plays a key role, in particular when we're talking about our binary acids. What other factors can affect our acidity? So we talked about bond strength, and that played a larger role for our binary acids than electronegativity. But let's not ignore electronegativity. Electronegativity does play a large role. So if we look at the first structure, that's acetic acid, the pKa of acetic acid is about 4.74, 4.75. Now, when we compare that now to chloroacetic acid, okay, so with chloroacetic acid, what we find is that chlorine has an electronegativity of 3 compared to hydrogen, which has an electronegativity of 2.1. So with the electronegativity of 3, we can see that it already has an impact on the acidity of my acid, where I went from 4.75 to 2.86. So chloroacetic acid is about 10 to the 2, 100-fold more acidic than acetic acid. Now, if we look at dichloroacetic acid, this has 2 electronegative atoms on that carbon compared to just 1. And again, it drops us approximately another 10-fold. Okay, so we went from 2.86 to 1.35. And finally, we can see with trichloroacetic acid, remember, we're going through the bond. This is an inductive effect. But basically, by having 3 electronegative groups here, we can see that I went from total 4.75 in acetic acid, replacing all my hydrogens now, to 0.66 for my pKa's. So that's quite acidic. All right, so electronegativity has a huge role in terms of when we say what affects our acidity. Finally, let's take a look at electronegativity in this fashion. If you look at carbon, nitrogen, oxygen, and fluorine, it turns out going from left to right here, I'm increasing in my electronegativity values. If you look at the acidity, this hydrogen is increasing in acidity as I go from left to right. So as my atom becomes more electronegative, the acidity increases. And if you look at the basicity, it's opposite. So when I have something that's very, very weak and weakly acidic, the base is very strong. So in a sense, you can say that the basicity for the conjugate base seems to be reversed in the trend. Okay, so again, we have the electronegativity example where we're looking at acetic acid derivatives. And we also see electronegativity as an example, just more directly attached to the electronegative atom. But there's one more factor that we want to be aware of, and this is a really big factor, and that's resonance stabilization. So whenever we talk about resonance, it's huge because it can explain a lot. And one of the things that it can explain is acidity. Resonance stabilization affects acidity. And one way that we often look at it is we're not directly looking at the acid, we look more at the effects on the base. Let's see what happened to this 3. The 3 got moved. Okay. So there should be a 3 down below. All right. So this is a CH3CH2O minus. This is my conjugate base of the acid ethanol. And what we find here for my conjugate base is that the oxygen is the one carrying that negative charge completely. And so you can see that the pKa is around 16. So about 100-fold less acidic than water even. But if we look at acetic acid, which has again pKa 4.74, 4.75, if you look at the conjugate base of acetic acid, you can see that my negative charge is now through resonance distributed across the 2 oxygens and the carbon here. And because of this right there, and because of this, now this conjugate base can be more stable as an ion. And so I don't need an H+, and so therefore it's more acidic at 4.74. Now, if you look at methane sulfonic acid, once I lose my hydrogen, I can now have 3 resonance forms. This negative charge, once I lose it and form my conjugate base, can be distributed across all 3 oxygens through that sulfur. And from resonance stabilization, now we find that this is a strong base with a pKa of negative 1.2. So these are some of the structural effects then that can affect our acidity. We have bond strength, particularly for our binary acids. We have electronegativity, where you can see it can be actually not directly attached or directly attached to the electronegative atom. So we have examples from acetic acid and its derivative, and we have examples going from methane all the way to hydrofluoric acid. And we see from resonance stabilization that because my conjugate base can be stabilized through resonance, that allows us to have a more stable dissociation. So then my acid becomes much stronger.